So, what are square symmetries and how can we use them in origami tessellations? That's exactly what I'm going to be talking about in this live stream today. And first, I want to go through some examples and some background so we understand why we even talk about symmetries when we're talking about origami tessellations. First, origami tessellations, which are each of these things in front of me today, are folded from a single sheet of paper by hand. This is a very long process, but definitely worthwhile in terms of the challenge in generating a pleasing result. So when we're folding origami tessellations, we want to pay attention to the features of the tessellation so that we can minimize looking at diagrams and maximize the flow of the folding. So we can get a sense for the tessellation and then just work on it and fold from there. So symmetries are what helps me the most to get a strong sense of the tessellation and what I'm going to be folding. So that's an introduction to symmetries. If you're interested in other kinds of symmetries, if you're joining me live here today, then you're going to see me coming out with these videos over the next few weeks. If you are watching the recording after, there's a link down below to see the whole series on symmetries. And let's dive into square symmetries in particular. So first I'm going to go through this big stack of tessellations, and we're going to notice that there's a lot in common with these tessellations, but there's also some things that are different. So first up, we've got this crossroads tessellation, and it uses multiple kinds of twists. Not all of these twists are themselves rotationally symmetric, but when you dive into it, you do end up having a rotationally symmetric form. So what do I mean by rotational symmetry? I mean there are multiple directions evenly spaced out from a given point that when you look at them look the same. So when I'm talking about square symmetries, I'm talking about fourfold rotational symmetries. Now these fourfold rotational symmetries, all the number fourfold means is that there are 4 of these directions that are evenly spaced out from a point that all look the same. And as we're going to get into today, that's not the only thing that we can say when we have a square type of symmetry. So looking through these, see if you can pick out some of these fourfold rotational positions. And it's not just wherever the center is. Since tessellations are infinite, these positions repeat at various points in the paper. And in square symmetries, there's going to be 2 different locations of fourfold rotational symmetry. So in this tessellation, it's called waffles, there's a fourfold position here in the middle of these right triangles, and a fourfold position here in the open square. But this square, even though the closed square twist all on its own is fourfold rotationally symmetric, happens to be in a position where only 2 directions going out from itself are actually the same. So this closed square is in a 2-fold rotationally symmetric position. And we'll see that again and again with each of these tessellations, that there's a fourfold position, a second fourfold position, and a 2-fold position that makes a right angle between the 2. So before we dive into close detail on all of these tessellations, and you can see it doesn't have to be done with twists, I want to show some of the math, some of the diagrams that I've developed on how we can figure these things out before we even start folding. So let's jump into it. Put these to the side. And really the order of operations here today is we'll look at square tilings, square symmetries, and then we will take a look at some of the properties of the square tiling. We can look at multiple applications of square symmetries on the same tiling, and then square symmetries on multiple different tilings. So let's jump in with squares, square tiles, and square tilings. So looking at this diagram, you see I've got a checkerboard pattern of squares here. And this is important. I have two colors because in origami tessellations, our twists have rotation directions. And each twist needs to have neighbors of the opposite rotation direction. So anytime I have a tiling of twists, and I'm not reversing any pleats between the twists, I'm just putting in twist, 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 and going twist by twist, not pre-creasing and collapsing, I need to have neighboring twists, neighboring tiles, in opposite rotational directions. So that's why I have the checkerboard coloring over here on the diagram. And we can examine this and say, okay, from a mathematical point of view, a tessellation is defined by the repeating unit. So what's the repeating unit here? It's actually not a single square. If this was not colored, it would be a single square. But since it's colored, the repeating unit of the tiling is actually 4 squares. 2 red and 2 white. So if I take these 4 squares and then copy them down, copy them over, copy them up, I've got the same groups of 4 squares everywhere that I'm looking at. So that's one of the key things with a tessellation, like what is my repeating unit? The next thing I want to look at here is how can we apply those symmetries I was talking about? The 4, the other 4, and the 2. So if I pull up my basic symmetry and zoom in here so that's easier to see, you can see I've got blue 4s in the red squares, gold 4s in the white squares, and then these gray 2s at all the corners of the tiling. And I've got a few tessellations with me today that follow that exact pattern. I'm looking behind me, cat's starting to climb on things. And let's take a quick look at how this pattern plays out in an origami tessellation. So I call this the alternating symmetry. And basically in this symmetry, you choose one twist, and then you choose a second twist, and you alternate between those two. So all the neighbors of twist 1 are twist 2. And in the simplest case, all of these are closed square twists. You just have some that are right-handed and some that are left-handed. So this central twist here is right-handed, and then that means these 4 neighbors of that central twist are all left-handed. And then these corners are right-handed again. So we see that checkerboard pattern coming up. We could make different choices though. We could alternate and have closed square twists in the middle, and then open square twists on either the front or the back coming off of it. So what does this mean with respect to the symmetry? Well, I can know that the center of my tile, aka the center of my twist, is a position of 4-fold rotational symmetry. So 4 directions off of the central twist have to be the same. And then my other tile, the open twist in this case, is also centered on a position of 4-fold rotational symmetry. So whatever is coming off of that open twist all has to be the same. So then I can read it and I can say, okay, I went from this central closed square to an open square. And then I can say, okay, that same relationship of closed to open is going to tell me the distance from open to closed in these other 4 positions, or sorry, other 3 positions around my open square. So you can see this is pretty powerful. Instead of having a whole crease pattern for one of these 2 tessellations, I can instead say, okay, I am centering on a closed square twist that is a position of 4-fold rotational symmetry inside the twist. And I am then going to put a open square twist next to it. And since that's 4-fold rotationally symmetric, I just have to define the distance to one of them. And in this case, I would say I am using tube pleat spacing. So this structure where we have a tube formed by 2 spaces between the same kind of fold in 2 different plates is what I call a tube. And that would be enough. And then the additional piece of information is that open twist on the same side or the opposite side as the closed twist. So really 4 pieces of information. Is my central twist open or closed? Is my outer twist open or closed? What's the spacing between those 2? And are these 2 twists on the same side of the paper or opposite sides? So with those 4 pieces of information, I can define any of these alternating square tessellations. And that's a lot less information than you see in a crease pattern, and it's a lot easier to use as you're folding. So when you have a pleat overlap between 2 twists, like say it's in this case between 2 open square twists, then I say, okay, I know that the neighbor of open square twists is a closed square twist, and it's going to be on the opposite side. So I'm going to flip to the side where that closed square twist is going in, find the 2 mountain folds of the pleat overlap, and those 2 at the intersection will tell me where the center of my closed square is. So you can see this is powerful for helping you to fold your tessellations as well. But back to the diagram. We can also, and actually, while we're here, there's the 2-fold rotational symmetry as well. Now it's not immediately obvious, but we do have 2-fold rotationally symmetric positions here. They're just not in the center of the twists. I have 2-fold rotationally symmetric positions here. So we've got 2 closed versus 2 open. Here, 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 really everywhere between or in the middle of a loop of 4 twists. And this is also true with these other 2 tessellations. So I've got these 2-fold positions here, and here, and here, and here. Notice this is not on a grid intersection in this case. I've got them here, and here, and here, and here. And using those positions is most helpful when you have extended symmetry with more stuff going on, kind of like the tessellations I was showing you in the beginning. So back to the diagram. What we've got now is the densest arrangement of these rotational symmetries on a square tiling. But there are other arrangements too. I can space them further apart, and in this particular case, I have an arrangement that I can bring up an example of from my stack of tessellations. And this one actually qualifies. So when we're looking at this tessellation, it's my fractured tiles tessellation, then I've got a twist with a fourfold rotational symmetry inside of it, in the center. I'm going to a twist on the back, and this is a hybrid square twist, so it doesn't look like it has twofold rotational symmetry in and of itself, but in the pleat pattern, it is twofold rotationally symmetric. There's just ambiguity in how you squash it down. And so that's our twofold position here. So I went from a fourfold to a twofold, and then I go straight back to another fourfold, and then I can continue looping around, and each of my twists has a rotational symmetric role to play. Now this is a particularly dense version of this tessellation. I could have chosen to give more space between the twists, but then you would get a different end effect. It would be, however, much easier to fold. You can also then space the symmetries out even further, because why not? When you do that, you end up with a tessellation like this, where you have some twists in positions of fourfold rotational symmetry, so here and here, some twists in positions of twofold rotational symmetry. And so let's say we're working with this one in the center, this one up above, and this one to the side. And you'll notice that there's more twists in between that do not actually play rotationally symmetric roles. And so this is one of the super cool things that I just figured out this year, that you can expand the symmetries on the same tiling and get these very interesting results. So that's as far as I want to go with the expanding symmetries. You can go even further on here, but I also want to show you some of the other tilings that can be used with this symmetry style. So we're not limited to just squares in square symmetries. We can also use right triangles. So let's take a look at this before I bring up the answers and see where are these positions of fourfold rotational symmetry in this right triangle tiling. I call this 8 and 4 right triangles. Is it in these loops of 4? No, because just like I was showing with us needing 4 squares that are alternately colored going around, and that gives us twofold rotational symmetry, this is actually going to be a twofold point because we've got 2 red and 2 white. Where we have 4 red and 4 white are these positions in the center of loops of 8. So if I bring up the symmetries, you can see there's fourfold in the center of loops of 8 and twofold in the center of loops of 4. And I do indeed have tessellations to demonstrate that as well. Let's jump over to those. So in the simplest case, when we're keeping these right triangle twists on the same side, we do end up with our fourfold rotational symmetries in the center of our loops of 8. And here you can see very clearly that these fourfold positions are different. So it's not just like with the closed square twist example that it's just in different rotational senses. You can have entirely different structures that are both fourfold rotationally symmetric. And then the loops of 4 that form the twofold symmetry are in between. They form right angles to the two positions of fourfold symmetry. And from the other side, these two positions of fourfold rotational symmetry are much less distinguishable. Now we have the same thing, again, all right triangles, same arrangement, but this time the twists are alternating front and back. And so we get these two different positions of fourfold rotational symmetry and a position of twofold symmetry. So there's one example of another tiling that you can do this with. Another example, we can bring squares back into it, but with right triangles beside them. And so in this case, what we're going to have is a very interesting symmetry style where we're functionally working in clusters. So you'll recognize the same loop of 4 right triangles that we said was twofold rotationally symmetric last time. And if we look diagonally out, we see 2 white squares going out, 2 red squares going out. This is a hint. This is a twofold position. And then the squares themselves, we can look in 4 different directions and see all the same things. So if we bring up our symmetry here, we see the fourfold in the red squares, the fourfold in the white squares, and the twofold, again, forming a right angle in between them. And we can take a look at a tessellation that matches the symmetry. In this case, we have mirror symmetry, just like we did with the closed square case, between these two different squares. So this one is left-handed, this one is right-handed, and we make a checkerboard pattern with these clusters where we have our fourfold rotational symmetry in all of these center of large square positions, and then our twofold rotational symmetry in the middle of these loops of 4 right triangles. But wait, there's more. There's always more with tessellations. And in this case, there's another tiling that I want to share with you. This one looks kind of crazy. It's a mix between several different tilings. So the large squares and right triangles, like we just saw, we have those same clusters here. The 8 and 4 right triangles that we just saw, we have some clusters from there as well. We also have these standard squares. So you can see these two are different sizes of squares. And that ends up being important for how to fold it. But that's not what we're talking about today. We're talking about the symmetry. And what we have here is fourfold symmetry in the positions that we pull from these other tilings. So in the middle of this cluster with the large square and 4 right triangles, in the middle of this loop of 8 right triangles, and then the small square acts as the twofold position. So I've got several examples of that tiling to show as well. Let me gather those. When you're showing a bunch of tessellations, everything gets all mixed together. So looking at this one, let's see if you can tell before I tell you. Did I start at a position of fourfold rotational symmetry in the middle, or is that a position of twofold rotational symmetry? So look top and bottom, look left and right. Is the top and bottom the same as the left and right, or are they different? In this case, The left and right are the same, the top and bottom are the same, but they're not the same as each other, so this is a twofold position. And the fourfold positions are actually these larger squares and the loops of right triangles. So next one up. This one actually is not the one I wanted to show, but I do have another one right here. And here I have a fourfold rotationally symmetric position in the center. I have more fourfold positions out here, so you can see these loops of 8 right triangles, just like we saw in this tessellation earlier. So side-by-side comparison, these loops are exactly the same as these loops. But instead of having all right triangles, we have these squares in the mix as well. So we've got 4 more positions that are the same as the center around the outside here. Now, where is my twofold position? Well, if I take 2 of the same fourfold and 2 of the other fourfold, and I see where the lines between them cross, that is my twofold position. And it turns out on this tessellation, that is a square on the back. Just amazingly cool. So one of my breakthroughs when I was teaching tessellations by tiles the other week on this tiling is that you can choose the cluster around the large square, the loop of 8 right triangles, and you can see when you're putting them together and you draw a line from center to center and then make a right angle that fits to the end of those lines. Can I put some kind of square twist at that position? And that is how you can easily generate new patterns. So these symmetries aren't just for folding, they aren't just for understanding existing patterns, they're also for designing new ones. So now that we've explored our square symmetries on the square tiling and how we can expand the symmetry to bring in different kinds of patterns. We've explored the square symmetry on multiple different tilings. So we have 4 different tilings, the squares, the 8 and 4 right triangles, the large squares and right triangles, and here the mixed squares and right triangles that all share this square symmetry. And now it's time to take a look back at those examples from the beginning and see if we can spot our symmetries as we go. So I'm going to start with the simpler tessellations and move us on up. Get these separated out. So we've got a closed square weave here. This might be the more common view of it. And we've got fourfold rotational symmetry in each of our square twists. They're alternating right and left-handed and forming that alternating checkerboard pattern. Next, I want us to look at another alternating square pattern where we again have fourfold rotational symmetry in the center of each twist. Now you'll notice this piece of paper isn't infinite. How can we say that things other than the very center are fourfold rotationally symmetric? Well, the tessellation itself is an idea more than it is the physical form. The pattern itself is infinite. There is no center of infinity. I'll let that sink in there. There is no center of infinity. And so we can talk about these rotational symmetries applying in multiple places of the paper other than just the center. So then, bringing in another alternating pattern where we've got our closed and our open square twists on opposite sides of the paper. Again, since this is an alternating pattern, the centers of the twists are all fourfold rotationally symmetric, and the center of the loop of 4 twists has twofold rotational symmetry. So left and right, same. Top and bottom, same. Right and top, not the same. That's twofold rotational symmetry. So moving on to our right triangle examples. We've got fourfold rotationally symmetric positions in the center of our loops of 8, and then twofold positions in the loops of 4. So even though this is a loop of 4, it's not fourfold rotationally symmetric. It's just 2. Because each twist in the loop is either right or left-handed. So there's 2 right-handed and 2 left-handed. Same goes if you put these same twists on opposite sides of the paper. We've still got our positions of fourfold rotational symmetry in the center of our loops of 8, and our twofold positions in the center of our loops of 4. Here it's really obvious because all of my twists of one-handedness are on one side of the paper and the twists of the other-handedness are on the opposite side. So you can see pretty immediately, like, oh yeah, this is 4, and this is 2. So next, I want to take a look at another large squares and right triangles tiling, tessellation. This one I call source and sink. And here our centers of fourfold rotational symmetry are in the squares themselves. So they are here, 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 but also the thing to watch out for, there's a closed square on the back here. So they're also here, 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 and here. And so you see this pinwheel pattern, and it looks fourfold rotationally symmetric in and of itself. Then you look up and down, you look right and left, and you see the same thing in all 4 directions. That is your clue to say, okay, that position is fourfold rotationally symmetric too. And when you flip it over, you actually get the same pattern again on the back. So that's a fun one. Another tessellation in this tiling keeps everything on the same side and has our fourfold positions again in the closed squares and the twofold positions between them. Now from the back, this is really clear which positions are the twofold and which positions are not. So the twofold positions have these arrows pointing in and pointing out, pointing in and pointing out. And so you might be thinking, well, if this is a twofold position and this is a twofold position, why are they not different twofold positions? These two look different to me. But if you're looking from the fourfold position, they look the same. So positions are different if they look different to the things around them. Continuing with the stacks of tessellations, we've got a closed square twist that itself is fourfold rotationally symmetric, but since it's in between 2 pairs of twists that are the same as each other but different from the other pair, that's actually in a twofold rotationally symmetric position overall. Whether it's a fourfold twist in and of itself or not, in this pattern, that twist is in a twofold position. So here we have 2 different kinds of closed squares. You fold them the same way. But this one is in a 4-fold rotationally symmetric position, and this one is in a 2-fold rotationally symmetric position. And when you're folding, you need to be aware that that is what's going on. Here, I already explained we've got the 4-fold position in the center and also in these open squares here. Now you might be saying, okay, what the heck is going on here? These aren't in the basic twist series. Well, these are double open square twists. And then on the back we have the hybrid square twists. And those are some things that I'll be covering in my upcoming Advanced Twist Techniques workshop. And there's all kinds of things going on. I also have a tutorial out already for the hybrid square twist. There's these two, these two that we saw with the mixed squares and right triangles tiling. And another one from that same tiling is waffles here, where we have loops of 8 right triangles with positions of 4-fold symmetry in the center. And between two of those, we have a position of 2-fold symmetry. You can use that to really cross-reference and find your other positions of 4-fold rotational symmetry. Particularly in this tiling, keeping track of which positions are what kind of symmetry is key to folding successfully. So I'm going to quickly flip through some more tessellations and see if you can spot the symmetries before I point them out. So here, I've got a 4-fold position in the center, and my next 4-fold position is out in this open square. So this is square knots weave, which is closely related to crossroads, which I've been talking about more this week. And you can see the same twists here. I've got the closed square, I've got the hybrid square, I've got the open square. And in this case, I have more twists in between. And the, okay, I'm seeing the comment now that the volume is too low to understand. Let me work on that, and I will make sure that it goes up with good volume. So we've got this twist going on, this twist over here. These same twists occupy the same functional roles in the tessellation, even though they form very different results. So next up, we've got this guy, another large squares and right triangles tiling. So we've got our 4-fold positions in the squares themselves, which are alternating right and left-handed, and then our 2-fold position in the center of the loops of 4. We can have alternating tessellations in more advanced twists as well. We can do that with these compound squares in multiple ways. And we can do this without folding twist-based at all. So these are actually isoarea closed squares in there. And we've got 4-fold positions here and here. And if I continued this, it would be in more locations as well. So one last stack of tessellations. Here we've got 4-fold positions here, and between, so at the crossing of the close spacings between the 4-folds, we've got our 2-fold. Here we have 4, 4, 4, 4. At the crossing, we've got the 2. Here also we have more of these isoarea closed squares, and we've got our 4-fold positions and our 2-fold positions in the gaps. We can basically go through these all day and see a variety of different tessellations. So one thing though, you might think that because we have all square twists, we're going to end up with a square symmetry, and that is actually not the case. We can use square twists in these cases in particular to end up with no 4-fold rotationally symmetric positions whatsoever. We can do that with the spacing. So these would be alternating patterns, but I've taken a cluster of 4 twists. So you can see 4 on the same side here, here's 2 on the same and 2 on the opposite, and then space them out, so all of a sudden there's no 4-fold rotational symmetric position in the center of the twist. The rotationally symmetric position is in the center of the cluster, not the twist. So we've got a 2-fold position here and another 2-fold position in here. So these two are analogous and these two are analogous. We also have a 2-fold position here and here. So here we're getting into tessellations, into symmetries with 4 2-fold positions instead of 2 4-fold and a 2-fold. Likewise, in here, we have these 4 2-fold positions as well. We have them in the center of this cluster, in the center of this loop, in the center of this loop, and in the center of this loop. And these are all 4 distinct positions. So there we've talked about square symmetries where they are and where they are not, different tilings that you can use square symmetries on, and different ways to apply square symmetries to the square tiling. So with that, I will leave you to your folding and see you next week. Happy folding!